Hi, now we're going to test claims about two means. So you'll be given two independent samples. So basically that would be like we're going to compare the age of men versus the age of women, or the body fat of Olympic runners versus body fat of Olympic divers. Something like that, but you've got these two independent groups. The claims are going to be about the mean, so mu1, mu2. In other words, there's not going to be a number in the claim. It's not going to say mu1 is 5 times bigger than mu2. It's just going to say, hey, these two groups are equal, or one is bigger than the other, something like that. So it'll be a direct comparison. So you're going to be given information, sample information for group number 1 and group number 2. So you will need the sample size, mean, and standard deviation. If you're ever given a choice, then you should choose group 1 to be the one with the larger mean. If you're not given a choice, it's not that big a deal, but if you have a choice, then choose group 1 to be the larger mean. And in case you love formulas, here's the test statistic. You subtract the two means, you divide by, etc. We're going to be using the calculator instead of the formula. Critical values, though, you do need to look those up in table A3. And degrees of freedom, well, there's two n's now. So you look at the smaller one. So I did say probably we're going to have this as the larger mean. That has nothing to do with sample size. It could be that N1, you have 100 men. N2, you have 500 women. Well, degrees of freedom is going to be the smaller of the two. So here, if this was 100, then degrees of freedom would be 99. So you go with the smaller one. All right, on to an example. So here are two people that are famous in baseball for hitting a lot of home runs. Barry Bonds, oops, I forgot to put a little asterisk by his name, and Hank Aaron's. So the data that I collected, so Bonds, about 21 seasons, and Hank Aaron back in the 50s and 60s, 70s, 22 seasons. So here's the claim. Look at, there's no number in the claim. It's just test the claim that they are equally good, that their average home runs per season is the same for the two. So here's what I found for Barry Bonds. His average is 36.286. Hank Aaron, 32.5. So I chose Bonds to be group number 1 because it was the larger mean of 36 compared to 32.5. The claim is that they're equally good, and by now I'm sure you've got it down how this works. This one's got to be the opposite when this says equals. This is now a two-tailed test, and we're going to be using T. So table A3 says we need to know degrees of freedom, so that means you take the smaller one, subtract 1, degrees of freedom is 20. With 0.05, you cut it in half. And with these videos, at least for right now, I'm not going to show the table because I'm sure you know how to use table A2 and A3 and even A4 quite well by now. Anyway, so this is what I looked up in table A3 and found the critical value to be 2.086. Okay, well, I'll do the formula one time, just for extra fun. So here's the formula. I found it to be a test statistic of 0.959. That definitely does not make it past 2.086, which means fail to reject H sub O. We cannot prove that there's a difference. So one thing you notice is that Hank Aaron has the smaller standard deviation. He was more consistent at hitting home runs than Barry Bonds was. You could read into why Barry Bonds was not as consistent, but we'll not go into that right now. So, what about the calculator? So you would need to go over to tests, and we're now at a two-sample t-test. Then type in the data. Notice that they put it in a slightly different order. The mean first, then the standard deviation, then the sample size. You do that for each group. And then continue down. Notice right here there's a little arrow. See the little arrow? So if you scroll down, or if you just hit enter on your calculator, you move down this. All of this is pretty much like we've been doing before. Here is something different. In statistics, they used to say, should we pool the two standard deviations? In other words, are these two close enough that you could just take their average and use that rather than using them individually? So you'd have to do this separate test to see if you can do that. And then you tell the calculator, yes, you can pool them, or no, you can't. Well, over the past few years, statisticians have decided, you know what, we're not going to do the pool thing anymore. Forget about that. We'll just use each standard deviation. Well, it seems that nobody told Texas Instruments because they still have it. So every time it says pooled, just say no. Okay, and then notice that the t is exactly the same as the formula, 0.959. So, failed to reject, we could not prove anything about these two players and their home run batting ability. Next up. Oh yeah, what about the confidence interval? So, for those that love formulas, here you go. So this would be the idea. You subtract the two means. So you subtract the two means to find out, well, what's the difference between the two players? And then, of course, there's going to be error. Add the error on one side, subtract it on the other, or use a calculator. So you go to test, but then scroll down to where it says intervals, and this one needs to be a t interval. Once again, just type in the data. And here is the confidence interval. And hopefully you remember, when there's a confidence interval and there's a negative on one side, a positive on the other side, that's the same as getting failed to reject. We did not prove anything. Because this side, the right side of the 11.777, that one is saying that Barry Bonds is better by approximately 11 home runs each season. The other side being negative says Hank Aaron is better. Well, which is it? Is Hank Aaron better, or is Barry Bonds? In other words, we cannot conclude. Okay. The next example, does having a filter on a cigarette lower the amount of tar? That's not good. Tar is probably not good to ingest. But anyway, test the claim that the non-filters are going to have. So you rip the filter off the cigarette, or it doesn't come with one, whatever. There's no filter on the cigarette, then the person would ingest more tar. So this is data that I found somewhere, and the data was set up like this. So I was not given a choice. This is sometimes going to happen. I was not given a choice as to which one is group number 1. Notice that this one, group number 2, has the bigger mean. That's not how I would want to set it up, but that's how it was given to me, so I need to deal with it. So test the claim that the non-filter, so this is the non-filter, so in other words, group 2, have more, so bigger than, group 1. That's going to make it a right-tailed test. Again, you go to the smaller of the degrees of freedom, so this one would be 17 and this one would be 20. You use 17 and use table A3, and you'll find a critical value of 1.740. Hey, this is supposed to say equals right here. I'm sorry, make that an equals. Okay, now watch what happens. So I do the, wow, that's a very big calculator you've got there. So I do the 2-sample t-test again. We type in the data. Don't forget to say no on the pooled. And now watch what happens. You ready? You gotta be paying attention. Watch. Ready? Ta-da! Look at the t. The t is a negative 11.897 negative. That means it goes to the left. That means that the t lands way over here. If the t is going to the left, this should have been a left-tailed test. So, by this being set up as this was the larger group instead of the way that I usually do it, and say group 1 should be larger, then that means I set up the claim wrong, because I set it up as a right-tailed test. But the test statistic, negative 11.897, that's telling me, this is right here, it's telling me that's supposed to be a left-tailed test because that's going to the left. So I should have set this up as the other way around. Put mu1 on this side. So you really, the final lesson right here is you always have to put mu1 on this side. No matter what the question really says, you have to set it up as mu1. So that would be group number 1. And then this would have to be less than. And when this is a less than, it changes it to a left-tailed test. So really this critical value should have been over here on the left as a negative 1.74. Then the test statistic of negative 11 would go way past that. So we did actually prove something. Or alternately, what you could do is say, if you didn't want to go through all of that, another thing you could do is say, you know what? What I'm going to do is just switch these two groups. And if you switch these two groups, excuse me, that wasn't supposed to happen. If you switch these two groups, then what happens is it turns out to be a positive 11.897. Then you get to keep your pretty picture. You don't have to change it. The 11 goes past the 1.74, and again, reject. So we actually did prove something. These two groups definitely are different, and it's because the non-filtered cigarettes have more tar. Okay, finally, what about the confidence interval? So when you look at the confidence interval, notice that this one is negative and this one is negative. When these two agree, then that means we definitely are proving something. So what this is saying is if there is a filter on the cigarette, there's going to be 8.9 milligrams less, so the negative means less than, or 12.67 milligrams less than compared to a cigarette with no filter on it.